Um, okay, I think maybe we could start now, Gabor. Today we have Professor Gábor Csányi to talk about the foundation model for atomistic chemistry. Gabor is a professor of molecular modeling in the University of Cambridge and is also a fellow of the Royal Society. I will leave this to Gabor, and thanks for your coming.
Hi. It was originally going to be a reading group rather than a formal seminar, and there's 7 of you, so maybe 8. I'm suggesting that I have lots of things in this talk, lots of examples, lots of things that should raise questions, and a little bit of technical stuff. So what I suggest is that I kind of go slowly. It doesn't matter if I don't get to the end, but I would really like people to stop me and ask questions. That's a challenge over Zoom, but I think otherwise there's not that much point. You can, if you want a straight up performance, you can go to YouTube and find essentially the same material. So I think it would be more interesting if we had more of a conversation prompted by my slides. So yeah, I don't know how many of the 8 people are willing to do that, but let's see. And because it's a small group, I suggest that you don't sort of put your hand up or something. You just unmute and speak. If that's all right. Yeah, so I turned on some more or less random, interesting slides from my slide deck. In materials modeling, there's lots and lots of different length scales and lots of different models, and I'm showing them a few of them here, and many of you will have heard of some of those, and they're not equally interesting, I think, from a machine learning point of view, but all of these are extremely widely used, depending on what length scale and what time scale you're interested in, and what sort of observable, what sort of accuracy you're after. So all the way on the left, we have quantum chemistry. You can do quantum chemistry on a couple of atoms really, really, really accurately. And it takes typically those methods don't parallelize very well, but takes a big fat node, and you can computer, and you can take a small molecule and compute its properties sort of exquisitely, accurately, more accurately than experiment in some cases. And I think that's where the biggest difference is when we do, as many of us do, and later in this talk, we talk about machine learning. But as we do that to quantum chemistry, that is the biggest difference that you should always bear in mind compared to doing machine learning almost anywhere else and for any other problem, is that here we actually know what the answer is. We can compute it. It's just that it's very expensive. So all of machine learning really is surrogate modeling when you talk about quantum chemistry and most of chemistry, I would say. The answers are there, whereas in large part of machine learning, for the classical topics of machine learning, image recognition, natural language processing, and so on, those functions that you're trying to approximate aren't actually real, aren't there in reality. You don't have the ground truth. You have data, you have classifiers, you have people assessing natural language, think, oh yeah, this is good. But that's a very, very noisy, very statistical oracle, right? It's not a sort of fixed thing. Whereas in this kind of simulation science, we actually know these functions. And I think this difference has shaped dramatically the failures and the successes and the attitudes of people who are trying to do machine learning for chemistry. So that's quantum chemistry all the way on the left. And then all these other methods that many of you will have heard of, for example, density functional theory, are different approximations of that exact answer. So it's a numerical, not quite just a numerical approximation. Some parts of it are numerical, other ones are a bit less controlled, but still much better controlled than any other ML type approximation that we're going to make. So we know what density functional theory can and can't do. Although, if I get to it, I'll give an example of when that sort of DFT approximation is giving us a problem. And then on the sort of right-hand side of this diagram, you have these continuum methods, finite element methods, and discrete dislocation dynamics is sort of another finite element based continuum, partly discrete model of materials. And it's not clear at all that there's anything to be learned there, that there's any learning task there. Finite elements solves a PDE, and it does it extremely efficiently. And it's not clear that one can do better. So I'm going to focus on the atomistic. Oh, before I go over, look at the capability. So this is sort of a log scale. So when I say expensive, quantum chemistry is really, really expensive, and you can do small molecules. When you go to density functional theory, you can do 10 times as many atoms. And that's why lots of people use it. When you go to force fields, which is what we're going to try and do, make a surrogate model for density functional theory. But of course, there are existing force fields that are empirical. You can do hundreds of thousands of atoms, millions of atoms. So typically on the same, I'm talking about the same hardware. What can you do in an hour of compute? So the costs of these things is dramatic. So what can you do with quantum chemistry, or with the DFT approximation of quantum chemistry? It turns out quite a lot, especially if you don't want long time scales. But it's really is now regarded as a sort of a computational microscope to see inside materials. So, for example, you can compute a phase diagram. The phase diagram is a diagram that tells you the axes are conditions, so temperature and pressure, sometimes other variables like composition. What sort of atoms do I have? What kind of elements do I have in my box, in my experiment? And the phase diagram tells you what, in the very broadest strokes, what kind of material you're going to see. So is it a liquid? Is it a gas? Is it a solid? If it's a solid, is it a crystalline solid? What kind of crystalline solid it is? And lots of properties of materials then follow from that, and not just sort of follow from that, but if you don't know what phase the material is in, it's hard to even start thinking about what properties, actual properties you want to measure, or what are interesting properties. If I have a liquid, it's going to flow, and I might be interested in how fast is it flowing. If it's a solid, then it's not going to flow. It's a crystal, and it just stays. Atoms more or less stay wherever they are. So the phase diagram is sort of the beginning, the first thing you want to ask about the material. But if you look at these axes here, this is a phase diagram of carbon, and I have temperature, and it goes up to 10,000 K. Okay, that's hotter than the surface of the sun. But we might be interested in that. We might be interested in planetary science. We might be interested in materials in the middle of the Earth, in the core of the Earth, where temperatures can go up to 6,000 degrees, 4,000, 6,000. So in fact, it's unknown. It's not entirely clear what the temperature is in the surface of the Earth. We know the surface of the sun much better than the middle of the Earth. On the pressure scale, we have 0. This is in GPa, gigapascals. So 1 bar atmospheric pressure is 10 to minus 4 GPa. So this is an enormous scale. And at the middle of the Earth, you get to about 400 GPa. The middle of very heavy planets like Jupiter, you can go even higher. And we might be interested in how materials behave up to about 300 GPa. So about here, we can do laboratory experiments. Beyond that, we can't. So the microscope, the computational microscope, allows us to assess reality in a domain, in a situation where experiment cannot. And now the question you might ask, and how do we even verify our theories? Well, in this lower regime, in this kind of corner, one can verify. And density functional theory approximation turns out to be pretty decent. Here's a very different kind of system. It's ions in solution. So ions that don't consist of just one atom, but polyatomic ions. So essentially small molecules, but charged. And they're very important because almost never deal with a pure liquid, pure water. It's very hard to make pure water. It's always got something in it. And when it's got lots of things in it, many of those things are not charged, and they affect the properties of water. They affect the properties of water as a solvent. They affect the properties of water, of what happens to it when you drink it. They have biological effects. So, but you can do measurements and you can study the bulk material, but you don't actually know how experimentally. It's very hard to access the atomic length scale. So you don't know what these ions look like in terms of the structure of the molecules around them. What does the water, which is a highly structured liquid, what does it look like around these charged solutes? And that essentially the only way we know, the only thing we know about that, almost the only thing, comes from calculation. And DFT is quite accurate for these things. Here's another example where experiment, so the first two examples are where experiment and theory kind of complement each other because you can't go to the right length scale or you can't go to the right pressures and temperatures. Surface science is another area where experiment and theory complement each other, again, in terms of length scale, but kind of very directly. So what you see here is a microscope image. It's a transmission electron microscope image of the surface of titania. So it's TiO2. It's basically sunscreen. It's the white bit of sunscreen. And in white paint, you have this titanium dioxide. It's a very active crystal, actually, and it binds molecules, and those molecules can undergo reactions there. And you can see the individual molecules in this experiment. These are the molecules, but you don't resolve the atoms. So you don't actually see who's bonded to whom and what's the structure of that molecule as it binds to the surface. So for that, you need calculation. And the images on the right is an atomistic model of molecules bound to these surfaces. And you can use DFT to study the orientation and the way these molecules undergo reactions and so on. And this has been done for many, many decades. And you can see that actually these are examples, all of which are examples where you can realize the system in not too many atoms, maybe 100 atoms. You can count the number of atoms here. You have a bit of surface, a bit of a molecule. I don't have an example in the other two cases, but you can represent a solution, a small solute, and 60 water molecules. That's maybe 200 atoms altogether. So this is perfect for this kind of approximation. And by doing DFT, you can study many, many different properties. Stability, thermodynamics, dynamical properties, because you have a bit of time scale. You can get the trajectories, the motion, you can study the motion of the atoms for quite a bit. But not immensely long, but a few thousand steps, tens of thousands of steps. Catalysis, this is the reactions of molecules on surfaces and the efficiency of that, and specific catalysts catalyzing specific reactions has been a huge success for this sort of modeling. You can study drugs. So the physical properties of drug molecules, in how do they crystallize. When you take a tablet, you're actually eating a crystal of molecules. What do those crystals look like? What sort of reactions do molecules undergo once you eat them? How do you metabolize them? That's excretion of drugs is extremely important. All of those you can study. Of course, a huge area is semiconductor defects. I won't talk too much about that, but that sort of underlies the whole operation of silicon in your computers. So I want to talk about force fields now. So how do we extend these fantastic successes that DFT has given us to these higher length scales and longer time scales? So people have been making force fields, which do away with, they don't model the quantum mechanics, they don't model the electrons and the way the electrons behave in the solid, they just model the atoms. And typically they're empirical because they take some information from the lower length scales. So for example, you can make a force field that gets you the correct crystal structure between different phases of a material. But typically that's not enough. You also refer to real experiments. You create an empirical force field with, let's say, 10 parameters for the energy of your system. And some of those you must set asking, does it give me the right answer on the length scale of real experiments? Does it give me the right density? Does it give me the right solubility of my drug molecule in water? And so these empirical force fields have a hugely long history. They have a lot of success, but they are kind of sit in between the world of experimentation and sort of top-down modeling, and on the one hand, and on the other hand, actually trying to mimic the reality of quantum mechanics. And so what we're trying to do in my research group is to replace these force fields with machine learned force fields, where we give up this sort of top-down approach and we say, let's just take the quantum mechanics and try and accelerate it by, let's say, a factor of 1,000,000 by creating a surrogate model, but not fit it to experiment at all, but just continue on this path of approximating quantum mechanics systematically and rigorously as much as we can, and then see where that takes us. And it turns out that this approach solves a lot of the problems of empirical force fields, which I'll show you sort of qualitatively in a second. Are there any questions? Does anyone, think of a question. And does anything have I said, does that spark a thought? Or do you have a comment?
I have a question. Can you hear me?
Yes, go on.
Yes. Hi. So my question is that moving from density functional theory, you're trying to essentially, I suppose my question now is, has there been new science created? So I work in the field, and this might be a bit of a step forward, but from these kind of very accurate, realistic quantum mechanical approaches, to your experience, has there been kind of new sciences and major advances coming out?
Sorry, are you asking whether these quantum mechanical models, have they advanced our understanding of the world, or are you asking whether these models themselves have advanced recently, these quantum mechanical methods? Which one?
I think it's more of has worked from dense functional theory, and now more like machine learning potentials created new stuff for experimentalists, for example?
I think the answer absolutely is yes. But and I want to sort of underscore how good this question is in the end, right? Because you could think, okay, what is the purpose of science, right? One is to understand the world, but also increasingly so technologically create the world and change it. And so quantum chemistry has this dual role, right? So on the one hand, I want to understand what I'm seeing experimentally. And quantum mechanics is the only way to do that. So you take a molecule, you heat it up, it gives off light, and that light has, its frequency is not constant. You get peaks and troughs in the intensity of the frequencies of light coming from molecules. And it's very complex. Those spectra, as they're called, is very complex. Let's try and understand it. And quantum mechanics is sort of the only way to rationalize what you're seeing when you shine light, or when you get light from materials and molecules. And so when you have individual atoms, you don't need complicated theories. Well, you don't need complicated simulation, right? Right back to the 1930s, and even before, people have heated gases, hydrogen and helium, and they measured the light coming off, and they saw that the light is not uniform, not white, not all colors of the rainbow. They're just very specific frequencies. And if you look at what frequencies come off, they follow a certain pattern. And this was the birth of quantum mechanics, when people have understood those patterns, and you can do that analytically for the hydrogen atom. But anything more complex, more complicated atoms than hydrogen, heavier atoms or molecules, you can't do it analytically. So you need one of these methods to actually say, why am I seeing that pattern? And you can immediately turn this into technology, because you can say, I want to analyze what atoms or molecules I have in a sample. And many of those techniques that you have to analyze them, experimental techniques, can only be interpreted given calculation. So a good example is NMR spectroscopy. is an absolutely standard laboratory technique for identifying molecules and functional groups. And the way you know what you have, although you have tables, and those tables are now incorporated into software that analyzes this automatically, but those are calculated using density functional theory and various versions of quantum chemistry. So I think when we talk about measurement science, there is this very, very close coupling between calculation and our theory of how vibrations happen, which is effectively what light is. But also, there's another sense in which new science is being done, which is where understanding leads to new ideas, right? So that's different from interpreting measurement. And I think one of the big, a very big sort of exemplar poster for that is catalysis. So inorganic catalysis, right? Our changing chemistry is changing, broadly speaking, is to changing molecules from one to the other. And that can happen very explosively when it wants to happen. So you set fire to a vapor of petrol and it burns, and we use that, we harness that, that's fine. But actually, it's really cool to make molecules change into other molecules in a way which is not spontaneous. It doesn't want to happen. And that's catalysis, and all of our technological society kind of depends on it. The most famous example is fertilizer, is essentially derived from ammonia. how do you make enough ammonia? You make it from nitrogen, which is a very, very inert gas in the air. And you want to make a lot of it. What happens when you don't have enough of it? Well, you have to use the natural fertilizers, basically the poo of animals. And there's not enough of it to feed 9 billion people. So for the last 150 years, we've been able to make ammonia from nitrogen. And how do you do that? You do it with a catalyst. So that's a complicated material, but ultimately it's an inorganic crystal whose surface makes molecules undergo reactions under certain temperature and pressure conditions, which they wouldn't otherwise if you didn't have that surface. And understanding that process and figuring out what are the conditions and what kind of surface is catalysis science. And it's been kind of trial and error and experimental until the 1980s, 90s. But since then, it's becoming much more computational. So the idea that I can take a computer and understand trends, and then predict what kind of surface of what kind of inorganic crystal will catalyze what kind of reaction is one of these holy grails in its entirety. But there are very large companies and many research groups engaged in kind of understanding the detail of that. And it's a huge industry. I think that would be the big example. But there are sort of many others. So if you go to sort of any chemical company, any drug company, so that's the biologically active molecules, chemical company, inorganic molecules, any kind of semiconductor company, they would be always engaged in modeling quantum mechanics, kind of coupled with experiment. Very few endeavors do only one or the other nowadays.
Yeah, I mean, thank you very much. I think this is a really good answer. My question is that the coupling should be two ways, right? But I suspect the experiment feeding theory is kind of a bigger avenue than the other way around.
I think that changes. I think that you will find that if you look at sort of high-profile papers now, experimental papers that introduce new materials, they are now not so credible without the calculation. Because, I did this thing in a lab, I sneezed on this thing, I pressed it, I measured it, here's my result. What have I got? What was in your sample? If you don't know, you don't even have a scientific result. You're now going to make a guess on what was in your sample. And the next thing people will tell you is that thing new? Is it reasonable? Is it plausible to have obtained those results, given your idea of what's in your sample? Let's do a quick calculation. And so another sort of quite recent example is superconductivity. So, those are materials that conduct electricity without any resistance whatsoever. It happens to many materials below a certain temperature. And there's a huge kind of race or huge endeavor trying to come up with materials where this happens at higher and higher temperatures so that we don't have to cool the material so much. And to have a material that does it at room temperature would be society-changing discovery. And people are now proposing various materials, and there are famous papers that have been published and then retracted in this. And now if you say, here, I have an experiment, it shows zero resistance, this material shows zero resistance, nobody will accept that without calculation. Because there have been so many failures in the recent past, by people kind of screwing up the experiment or misinterpreting it or somehow rushing too early, right? If you spend 10 years studying the material, of course, experimentation can do everything, but you won't do that you want to publish in after 6 months, the first discovery. So your experiments are really crude and very uncertain. And so you have to actually back them up with calculation. Is that plausible? Is even the crystal structure that you're seeing, the conditions, under the conditions, do those atoms even plausibly do what you're claiming that they would do? So I think that's quite common now. Okay, I'm gonna just move on and then
Thank you very much.
again and ask people, prompt people to ask questions. So let me return to computational cost. So I said that DFT can do about 100 atoms, and that's on one compute node with CPUs, let's say, and it's 1 hour. The real difficulty is not is partly the absolute time, but also the bad scaling. So it scales cubically with the number of atoms. It's for metals, that's certainly true. There are algorithms that scale more favorably, but their prefactors are much larger. So this is still not a bad number to bear in mind. But that's the kind of lowest quality DFT. If you want a real high quality calculation, that scales as n to the fourth, so the number of electrons, but typically number of atoms also, with the fourth power. So that's why I made that slide with the capability 20 years ago, and I put 100 atoms, and I didn't really have to change that very much because no one nowadays you can do a hero calculation with 1,000 atoms or a few thousand atoms, but you're only going to do 1 or 2. You're not going to do many such calculations because yes, computers have gotten faster, but not at this not at this rate. So and computers have gone, Moore's law is about parallelism, not about clock speed. If you want to do the gold standard of quantum chemistry, it's called coupled cluster theory, and that scales as n to the 7. So you're going to do very small molecules. Essentially, that's it. And this is the usage histogram of the UK's national supercomputer. It's now 4 years. This particular one is now 4 years out of date. Up to, I checked it last year, it's about this, it hasn't changed. It'll be very interesting to see what happened next year. But this code, VASP, it takes about 35% of Archer 2, is the biggest computer in the UK, biggest academically accessible computer. And almost all of this is doing molecular dynamics using the density functional theory. So most academic compute in the UK is going towards this, using quantum mechanics to simulate materials in a dynamical fashion. So what happens when you actually do that? It's called ab initio molecular dynamics, and you have atomic positions, or you start off with the atoms somewhere, then you solve quantum mechanics in this approximation that takes you 1 hour for your 100 atoms, and from that you derive forces on the atoms, like which way do those atoms want to move, and you plug those forces into Newton's law, right? F equals ma. You get the forces, now you get accelerations, r double dot. You update the positions by a very small amount, and you go back to solving the quantum mechanics again. And in some sense, this is, you're simulating how the world really is. This is how real materials operate. But it's kind of wasteful because in the long run, you're just keeping track of trajectories, forces, and positions. But in order to compute those forces, you're doing this very, very expensive calculation. You're computing a lot of auxiliary quantities, basically electrons, electron densities, wave functions. And all of that is being thrown away. And if you think of in terms of the amount of data, the amount of data that goes around here in Newton's law is 3 numbers per atom. Position, XYZ, forces, XYZ. But the way you get those positions, you're solving the Schrödinger equation for electrons. Each one of those electrons has an orbital that's a density field in real space. So it might have 10,000 values in your box. That's 1 electron. And for each electron, and there might be 1,000 electrons in your system, you are storing or you're computing a density field in the entire box, right? So many, many gigabytes of data that you're handling, you're conjuring up, you're solving this high-dimensional PDE, that's a Schrödinger equation. You're then measuring from that 3n numbers, couple of hundred numbers. You're throwing everything away. So this is what makes this process, this is what I've just described, makes it the absolute prime target for making surrogate models, right? What we want to do is go from positions to forces directly, kind of analytically, without having to conjure up gigabytes of data, which is reality. Electrons are real, wave functions are basically real, but it's extremely time consuming. And this is what gives rise to that sort of hard wall in capability when you're doing real quantum mechanics. So really what we want is a map from the positions of atoms to forces, or rather, actually, I don't want forces, I want the energy whose gradient are the forces, right? So I want the potential energy, V of R. R here is kind of a generalized coordinate, the 3n positions of n atoms, and the gradient of that V are the forces. And so I want a map from R to the 3n to R. And that is a very complicated map. I can compute it for any R very, very expensively, but I want to build a surrogate for that. And the question is, okay, this sounds like a brilliant idea. Did I just come up with it? Or did people come up with it 20 years ago? The answer is, of course, not. Quantum chemists have been doing this for a long time. Again, for very, very small molecules. For the small molecules for which you can do quantum chemistry, people have been building maps with very systematic manner, in a manner that scales exponentially. So you can go back in the literature and find people explicitly writing down maps like this, but they can only do a dozen atoms. So the big question for the ML literature, or the ML literate people 20 years ago in my field, was can you build such maps for materials, not just for small molecules, and for molecular assemblies. So for basically things that scale, where you have 100 atoms, 1,000 atoms, 10,000 atoms, a million atoms. Can I make a map like this that's kind of credibly accurate? And you want to do simulations. You want to do accurate simulations like this, what the quantum chemists are doing, but you also want to do simulations like I have on the right. So this is a dynamical trajectory. I call this the baby battery. You have these big purple blobs represent lithium ions, and they're in your lithium-ion battery. This is graphite. That's the anode of your battery. And on the right, you have some nickel cobalt oxide, which is the cathode of your battery. And you want to simulate that sort of process. Now, this is what I've shown you here is a super oversimplified simulation. The real battery simulation would need to be orders of magnitude bigger. But even this you can't do with quantum mechanics. It's too big. This has a couple of thousand atoms in it. And you can't do that with density functional theory. It's too big. And you don't really have force fields that do this in their full generality. So the ML potentials, ML surrogates to quantum mechanics, have been built, and that's what people in my field do. And here's a sort of graphical history. So before 2007, people have made surrogate models of essentially a single mode. You can think of what I'm drawing you here is the energy, but the probability density is, is the Boltzmann distribution, e to the beta e. So every time I have a trough in the energy, you imagine a huge peak in the probability distribution. And you go to one of those peaks that could represent a molecule, or it could represent a crystal. And I can regress the potential energy around that mode. And people have been doing that. Those were the low dimensional fits. Not particularly useful. I wouldn't say new science can be done with those things. And then the kind of breakthrough that really happened was in 2007 with high-dimensional fits. So computers getting faster, bigger fits can be made, more data available, people, physicists and chemists learning about neural networks, sort of coming out of the AI winter of the 1990s, still using very primitive sort of feed-forward neural networks. But, and I'm going to show you what kind of descriptors they use, and that was the key. People are able to fit multiple modes. And that is already useful. You can make a model for a specific system, for a specific material, collect lots of data, spend 2 years honing your model, validating its accuracy, and then you can do try and do discover some new science, do something new for that system. It's still kind of hard to do new science in this way because you spend so much time studying those few modes that it's going to be hard to say that you have new science. But you can certainly, people have done that. And the real interesting thing in the last couple of years is wide transferability. So extreme generalization. The kind of generalization that I suggest hasn't really been seen in traditional ML. So the question is, so the idea is that you train on very, very few, not single mode, but very few modes in a very, very restricted part of all possible materials. You train a model, and that model now basically does the right thing. Not precisely, doesn't get every mode right, doesn't get necessarily every observable that you're interested in right everywhere, far, far away from your training set, but does a credible job in a way that accelerates your workflow tremendously. And if you really, really care about some other kind of mode, then you take new data there, and you know how to do that because you have one of these widely transferring models. So you can run simulations and obtain data here. And remember, we're building a surrogate, so I can always compute new data. And then you fine-tune. So then you fine-tune your model and become accurate there as well. And that's the sort of most exciting thing. I now see that because I want this to be more pedagogical, I'm probably not going to reach that in this talk. We can do a second round another time. When we do this kind of fits, so we do a fit for the energy and ultimately use its gradient, I want to impress upon you the challenges of doing of the kind of accuracies that you need when you make such a fit. And the requirement for accuracy comes from the fact that we're going to do molecular dynamics. We're going to use Newton's law to solve the time trajectory. So, and that time trajectory needs to be accurate in the sense that it needs to give accurate averages. And this kind of simulation is inherently autoregressive. So you can if you make certain kinds of errors, the errors in your observables are exponentially large in the errors that you make in your model. So think of this autoregressive simulation, Newton's law, iterated. You very rarely are interested in less than 1 million iterations. And so what ends up happening is that you need to fit the energy of your system, so that's the log probability, to about 1 part in 10,000. 99.99% accuracy. Models aren't really that useful if they don't have that accuracy. And we can also say what you need on the forces, so that's the gradients. You need about 95 to 99% accuracy on gradients. And because that controls the dynamics. The energy controls overall accuracy. And this is why this is very hard. This is what I'm showing you in these graphs are examples of why you need such accuracies. Apart from, even if you weren't autoregressive, just to describe different phases of materials. So here I have 2 carbon atoms, and this is the red curve is the energy as a function of distance. And I'm now getting you used to different units. So this is interatomic distances in angstroms, and this is the energy in electron volts. And you want to describe this fact that these two carbon atoms bind, and the binding energy is about 4 electron volts, and the repulsion goes up actually arbitrarily high, but you know, I go to half the bond length from the minimum and I get to 10 EVs. So that's a typical size. I want this function to be regressed to about 10 EV. But if I go to graphite, which is a layered form of carbon, super important, super interesting as a physical material, the interaction between those layers that gives the interesting properties of graphite, that it's so soft, are very, very small. So the binding energy between these two plates of carbon atoms is about 0.03 electron volts. Okay, so, and then there is the repulsion if I press those plates together. So, and it goes up to, you know, 0.1 electron volt. So if you accept that we want 99% accuracy, let's say I want 99% accuracy on the energy here, then I want that in both situations. So unless you somehow arrange it so that the model is very much more accurate here than here, if you have uniform accuracy, because you don't know ahead of time which part of phase space we're in, then you take the accuracy, the permissible error here, and you divide it by the absolute value of the function here. And you get this factor of one part in 10,000. So there are other aspects of the potential that we really want. We want symmetry, so that's equivariance in the modern parlance. We want translational, rotational, permutational symmetry. And lots of people are trying to give these up and seeing what happens when you do that. But I think it's good to start from why these symmetries are interesting. The real potential has these symmetries. The quantum mechanics has these symmetries. And I'm trying to build a surrogate here, so which is super accurate. So before we give them up and see whether what happens when I have models that don't obey it, let's try and this is certainly what people did in the first 15 years, make models that actually obey these symmetries. And that turns out to be kind of tricky. Translations are actually the easy one, where each atom is going to have an energy as a function of its environment. And I'm just going to evaluate that function for each atom. Clearly, it's enough to talk about relative positions. And now I have translation invariance. Rotational symmetries are harder, because if I rotate my whole environment, I want the same energy. So I can't use essentially Cartesian coordinates as my inputs, because they are not rotational invariants. And permutation is the order in which you list the particles. And you want that kind of symmetry because it's kind of intimately tied into continuity. So imagine that my atom only knows about the other neighbors nearby. As those nearby atoms leave, I want the function not to care, and that atom can come back somewhere else. And so essentially I can reorder the neighborhood of my atoms, and I want continuity there. If you don't have continuity, it's going to be really hard to perform a dynamical simulation, because you have a discontinuity in the potential, gives rise to formally an infinite force, lots and lots of problems. So this sort of task of coming up with an energy of an atom as a function of its environment has close analogies to other problems that you might be familiar with. So the problem of molecular structure and coming up with descriptors for molecular structure for not this task, but statistical learning tasks is very, very analogous. There's lots of similar mathematical problems here, symmetry and so on. 3D point clouds and doing traditional machine learning on point clouds and saying I'm trying to do classification, recognition of 3D objects and so on. Translational, rotational, permutational symmetry is part of that task as well. And soon we're going to talk about graphs and representing inputs as graphs, spatial geometric graphs. And so the graph isomorphism problem, which is essentially has the permutation problem inside it, is also analogous. And some of you might have heard of the Weisfelder-Lehmann test, and that's an interesting, again, a different kind of problem, which is, can you solve the graph? Is an algorithm for the graph isomorphism test, and it's not a perfect solution to it. There are graphs where the Weisfelder-Lehmann test passes, but they're still not isomorphic. But it's a very sophisticated test, and it turns out that it's worth studying graph isomorphism in its abstract, because the best performing models for molecular machine learning and material machine learning turn out to have very close analogies with what the Weisfelder-Lehmann test does. So that's an interesting correspondence, and it's an interesting piece of literature to become familiar with. So,
sorry, can I ask a question?
Yes, please.
Yeah. So you mentioned that you would want your network to be physically informed.
I didn't use that word, but sure.
Sorry, I mean, it have similarities with how DFT would be doing things and so on. Are there, to your knowledge, any networks, any machine learning potentials that still don't try to be physically informed,
of course,
or that are they
I
still
think there are sort of
heavily applied, or?
Well, there are sort of two classes of these. The very early stuff, pre-2007, when people didn't know how to make representations of molecular structure and atomic neighborhoods, which are rotationally and permutationally invariant. So that's a hard math problem. If I ask you, and again, it's shared with the point cloud. So if I say, give me a description of, here are some 3D vectors, give me a description of the positions, the relative positions of these vectors, such that that description is rotationally and permutationally invariant. That's not an easy task if I also demand continuity and if I also demand completeness, so that only one descriptor, so that if you have two different structures, they have different descriptors, right? You could take the distance to each of these atoms and sum them up, and that's a rotationally permutationally invariant descriptor, but it's very poor descriptor. It doesn't discriminate, right? So early on, there were descriptors which didn't satisfy these requirements, and so people made models that way, and they didn't work very well. And very recently, in the last few years, with enormous amounts of data, enormous amounts of nonlinear modeling, deep learning, people are now asking, can I give up this task, this requirement, and just make sure my models do well by doing data augmentation, by sort of dumping enormous amounts of data into it, and let the machine learn these symmetries. And you hope to do that. Why would you do that? You hope to do that so that your inference is faster, right? So if your inference is not faster, then you've kind of given up an exact property of the quantum mechanics for a kind of no gain. So I think that's, and yes, there are a few groups around the world who kind of really understand this and try to make very fast models that don't, but they have not seen so much use, I would say. But it's certainly it's a legitimate activity. It's just that the biggest kind of breakthroughs in terms of usefulness and the most widely used models that specifically in the force field business have been the ones that allow symmetry, that obey symmetry. And one interesting reason for this also is that it's clear to everyone that if you're going to try and learn symmetries, you have to have immense amounts of data. And it's not clear that you have that much data, especially when you try to go beyond DFT, when you try to go to those higher levels of quantum mechanics. Well, but then maybe you could do multi-fidelity learning, where much of your data is lower quality, but it's a huge amount, and your system learns the symmetry from that. So there's lots and lots of possibilities. I sort of run out of time, and I'm kind of halfway through the talk because I deliberately wanted to make it very slowly. So I'm just going to go through this one slide just to end on something technical. And if you guys want, we can have another session where we catch up with the further developments, GNNs, and so on. But let me show you how the rotational and permutational symmetry problem was solved in 2007, between 2007 and 2010, which then kind of gave rise to this whole modern ML force field business. So these are the three symmetries that I want. And the first solution to it came from Jörg Behler and Michele Pernello in an extremely well-cited paper in 2007, and that's where the date comes from. And it's an extremely physicist's solution. So you take, the task is that you have neighbors at positions Rij, and you want to make rotationally and permutationally invariant this representation from it, and you hand design it in the following way. You first you have two batches of disk representations. The G2 is going to focus on pairs of atoms. So the first one of the pair is the middle one, the central one, and the other of the pair that's atom I, and atom J is your neighbor. And you're going to put the Rij, the length of your bond, into an argument of a Gaussian, and Rn is kind of the center of that Gaussian. And you can have different Rn's, and you can have different widths of these Gaussians. And so taking these different etas and different Rn's, you can generate a whole bunch of 2D, one-dimensional representations of how far are my neighbors. And you can easily understand that this is some sort of smooth version of a histogram of how far my neighbors are. And that's it's a good but very poor descriptor on its own. The insight of these guys was that you can augment that with a sort of a three-body this representation, which takes atoms I in the center and JK that are two of your neighbors, and you use this formula. So you take the angle theta ijk, you make a polynomial with some lambda here of the cosine of ijk, you raise it to some power, and then you do some kind of cutoff so that as you take the distance far away, this descriptor also goes to 0. But the key, so ignore this exponential, the key part is kind of here. And this is sensitive to the angles between your neighbors. And they were extremely successful in using these pair of descriptors to feed them into a feed-forward neural network and regress the potential energy. Let me show you what looks like a completely different kind of descriptor made around about the same time. This was our work. And a few years later, we learned that these are more or less equivalent. So but it's interesting to do this for what comes next in the development, because this guy on the left doesn't really generalize. If you try to generalize it, it becomes very, very expensive. Whereas the thing on the right generalizes easily and has been generalized and is the foundation of what people use nowadays. So here you start by putting a Gaussian not on the distances like here, but on the actual vectors. So bold R is a vector here. So imagine that this rho is like a density of neighbors in 3D. You put a Gaussian on each of your neighbors in 3 dimensions. And then you expand that density in a basis. So YLMs are spherical harmonics and Rn is a radial basis. So this is just a basis expansion of a 3-dimensional density of neighbors. And the C's here are expansion coefficients. And they have these indices NLM corresponding to the basis functions. And it turns out that if you square these these expansion coefficients, you get a descriptor which is called the spectrum, the spherical spectrum. It has 3 indices, N, N prime, and L, coming from the basis indices. And it's an excellent representation. So this PNN prime L for atom I in the center is a really good representation. You can feed it into a neural network. You can build a kernel out of it, so a linear or a polynomial kernel. And calculating this scales much better than the representation on the left. So here, especially with the number of neighbors. So here you have a quadratic scaling with the number of neighbors because this is a double sum. And here you have a single sum over neighbors. And then there is the basis expansion, but you truncate that at quite low NLM, and that truncation kind of stays fixed. So you can evaluate it for 40 neighbors or 100 neighbors, and this would be a sum over 10,000 elements. And here it's just a sum over 100 things. And much later, we learned that there's a correspondence. So you can actually, if you don't do the truncation in NLM, and you take an enormous number of different etas and RNs and lambdas, you take the limit of these descriptors, they kind of do the same thing. So you can compute the G2 from this basis expansion, the C's, and you can compute the G3 and vice versa from the power spectrum. And that was kind of understood around 2014, 2015, that in the limit, you can really compute one from the other, but they're different discretizations of the density. So actually, I'm going to finish on this slide. So what I want to show you is what kind of amazing difference either of these methods have made to materials modeling, which really had only empirical potentials up to now. So what I'm showing you here are errors with respect to quantum mechanics of 3 different empirical models, so 3, 4, 5 parameter models that were made, 30 years apart. And the errors are kind of bad and they don't improve. And the moment you turn on an ML-based surrogate, this is based on the right-hand side, but it could have done the left-hand side descriptors either. Jörg Baylor Parnell descriptors are fine. We use the bispectrum or the spectrum, the spherical spectrum, and you get these red points. And you just nail it. And this is the moment which you know from the culture of machine learning. This is when machine learning comes and eats your field for lunch. When you just turn on the first time the sophisticated ML technology, in this case, feed-forward neural networks or kernel methods, but many parameters, many tens of thousands of degrees of freedom, highly parameterized, richly parameterized models. With the right descriptor, you just nail it. And these are downstream observables. This is not an energy of an atom. This is elastic constants, how soft a material is. What is the surface energy when you break a crystal? These are kind of complicated observables, the kind of things you want to compute, the kind of things you want quantum mechanics to predict for you, and you get it. You get it right. So let me stop here, and we can, if you guys are interested, we can continue. If you have any other questions, I'm happy to answer for a minute, but actually, I then need to go to another meeting.
Actually, I have one question,
Okay.
but I think this question is not that related to like the force field one. So you mentioned about the data augmentation in machine learning force field. So I'm wondering, like, when people do like the structure prediction. So for example, like AlphaFold, they predict the molecular structure or the protein structure using neural networks.
Yeah.
People usually do data augmentation here. So do you have any comments about this? Do you think like if I'm doing structure predictions, I use data augmentation, is it the correct
Structure
one?
prediction is very much a top-down modeling. You're not trying to do an autoregressive model, or not for millions of steps. And you're not trying to compute very, very, very sensitive averages over a very large number of samples. So I don't see any reason not to do data augmentation, especially when your model is like, you know, a diffusion model, very, very nonlinear, very, very scalable to very large data. And you're not trying to do a simulation. You're not actually trying to do a surrogate. You're doing density estimation, and you're not doing Boltzmann. So if you were trying to, let's draw the distinction between structure generation and kind of Boltzmann sampling, right? If you were trying, if your pure goal is to come up with approximate positions to drive other downstream activity, I don't think there's anything wrong with getting them a little bit off. Diversity and robustness much more important than the detail, and you don't have good descriptors necessarily. The descriptors that I've introduced, permutational, rotational, invariant descriptors, they don't work for 1 million atoms in a protein. They are local. They work for 100 atoms. So I wouldn't even know how to do it, how to build such descriptors. Now, you could say, okay, I'm going to make my model equivariant. But if that's going to stop you from doing the huge training that you need to do, I don't see why in the actual inference it's going to really help you. Whereas in simulation, when you're doing molecular dynamics, I think the symmetries are really helpful. And when you and when you're trying to capture averages over very long trajectories. So I think that's the big difference.
I see. Thanks.
And these things could merge. I mean, those are the differences as I see them now. Okay, I better go to my talk, to my meeting. That's also on.
Okay. Yeah.
Okay.
Yeah. Thank you very much today. Okay.
Bye.
Yeah. See you.
Bye.
Bye, Panos.